All right, welcome to section 9.4. This is on indices, aka discrete logarithms. So if you wonder why we're missing or why we're skipping sections 9.2 and 9.3, this is because those two sections basically concern themselves with finding primitive roots and whether primitive roots exist, and so they're fairly technical. So we're just going to skip those and jump to 9.4, which addresses like what can we actually do with primitive roots. So let's say sections 9.3, 9.2, let's say address the existence of primitive roots. And are quite technical. So we just want to look at what we can do with them. So we're only interested in what we can do with them. So what we want to address in this particular section then specifically is, so in regular arithmetic, like non-modular, we can write the following. We know the following is true. We know that r to the x is a equals, this is if and only if log base r of a equals x. So then, and this is useful for solving equations, right, involving exponents, especially when the variable is in the exponent. So if you wanted a modular arithmetic version, we could say, how might a mod version work? In other words, you might have something like r to the x is congruent to a mod m if and only if what? Like what goes on the right hand side that could be useful. So it turns out this isn't quite as easy as in the non-modular case. So we need to sort of look at some very specific cases and methods. This is not as obvious as this case right here. So we need to sort of zoom in a bit. So we'll begin by looking at the idea of indices, which are discrete logarithms. You can use either term. The book uses indices, so I'm going to stick with that. And for the intro, what I want to do is I want to sort of point out what we can do with a primitive root. Now this is something we've seen already, but it's worth revisiting. So given a modulus m, this is like a little intro for this, m, and a primitive root r. So we know that if we take all the powers of r up to and including r to the phi of m, this gives us a reduced residue set mod m. So this is reduced residue set mod m. Remember, this means, let's say, meaning up to congruence mod m. This gives all integers coprime to m. That's sort of basically the way you want to think about it. So for example, r equals 3 is a primitive root of m equals 14. So we can verify that by checking out all the powers. And it's worth doing this because it also helps us sort of see what the statement has just said. Right? So if we take 3 to the 1, we get 3. If we take 3 to the 2, we get 9. If we take 3 to the 3, we get 13. 3 to the 4 is 11, 3 to the 5 is 5, and 3 to the 6 is 1. These are all mod 14. And if you notice the list of outputs, right, we got basically 3, 9, 13, 11, 5, and 1. This is everything that's co-primed to 14. Up to congruence, or equivalent if you like, mod 14. So for example, I have 1, I don't need to list, say, 15 separately because it's congruent to this. And of course, this also shows that 3 is a primitive root because 3 to the phi of 14 is 1, right? It's sort of the lowest power. So note that we also see that r equals 3 is a primitive root, like we claimed, mod 14, because the order mod 14 of 3 is phi of 14, which is 6. In other words, that's the first power that gives us 1 right there. So at this point, we can sort of see something that sort of addresses this statement back over here a little bit. Right? So this is what we see, that the following is true. Right? Like in this particular case, right, or in general, right, we can say that r to the x, let's do both. In general, r to the x is congruent to a mod m has a solution if and only if a is coprime to m. So for example, if you look in the above, we could say like 3 to the x is congruent to, say, 13 has a solution because the GCD of 13 and 14 is 1. But for example, 3 to the x is congruent to, say, 4 does not. So this leads to being able to give a definition, right? So we can give a definition of what this x would be, which is sort of like a logarithm. So in other words, we get the following. So B, we get our definition. So think about this example on the right as we do this, and then we're going to revisit this example on the right. So if r is a primitive root mod m, and if the GCD of a and m is 1, then the exponent x with x between 1 and phi of m satisfying r to the x is congruent to a mod m. This is called the index of a mod m with base r. Now, just for reference, the with base r is optional. Like, you don't need to say it, but it's implied in this case. But really, it's sort of this entire thing. Sorry, I got some crap here on the page. This is AKA the discrete logarithm of a mod m with base r. And this is denoted IND sub RA, which is even sort of a little more confusing because there's no M in the notation, right? So here M is contextual, like you sort of have to know, and you will know what the modulus is that you're talking about, right? So just to sort of nail down an example I'm going to take all these things over here on the right, I'm going to rewrite them, and I'm going to write the equivalent statement, and then it should make perfect sense, right? You'll sort of see what happens. So 3 to the 1 is congruent to 3 mod 14. So this tells us that the index with base 3 of 3 is 1. 3 to the 2 is 9 mod 14. This tells us that the index base 3 of 9 is 2. So basically it's like a logarithm. 3 to the 3 is congruent to 13 mod 14. So the index base 3 of 13 is 3. 3 more, so it's worth listing them all. 3 to the 4 is 11 mod 14. So the index, badly written, the index, wow, I can't write today. The index base 3 of 11 is 4. 3 to the 5 is 5 mod 14. So the index of 5 is 5, and 3 to the 6 is 1 mod 14. So the index base 3 of 1 is 6, right? So these all look like logarithms. All right, so for like, if you look at the second right here, you could, like the logarithm equivalent might be like 3 to the 2 is 9, so the logarithm base 3 of 9 is 2, which seems to make perfect sense. So hopefully this sort of looks like logarithms. The reason we don't use log is because it's modular arithmetic. So by writing index, by writing I and D, it sort of makes it much more clear what's going on contextually. So the first thing to note is two things fall immediately out of this definition. So immediately we get the following theorem. I'm going to call it a theorem just so it carries some weight, but really it's just the thing that follows, obviously. So if A and B are coprime to M, and if R is a primitive root, mod M, we get two things. The first thing is that R to the index base R of A is A, which makes sense because the index is basically saying what power do you need to raise R to get A, and then you raise R to that power, and of course you get A. And the second thing is that A is congruent to B mod M if and only if the index base R of A is the index base R of B. And this makes sense too, because basically saying if the powers are the same, in other words, if the power that you raise R2 to get A is the same as the power that you raise R2 to get B, then A and B themselves are the same. Now I want to make a little note here, and again, you can see this back in the previous example, right? You could see, for example, that let's say, for example, let's look back at the previous one, right? Say 3 is congruent to 17 mod 14. And the corresponding statement is that the index base 3 of 3 is 1. And the index base 3 of 17 is 1. And this thing is simply because 17 is the same as 3. In other words, what do you raise 3 to get 17? Well, the same thing that you raise it to get 1, right? Because 3 and 17 are the same. Right? Now, just a little note here. This is a note about this statement right here. So because indices are always between 1 and phi of n, inclusive, in other words, they can be equal to those. So we can write the following. Let's say we'll write A is congruent to B mod M if and only if the index base A of A is congruent to the index base sorry, R of A is equal to the index base R of B mod phi of M. This may seem a bit weird to write this because they're equal, right? They're not just congruent mod phi of M, but it turns out to be useful when we do some index arithmetic later in the lesson to have it this way. So I'm going to put a box around this just to sort of keep this in mind as we go forward. All right, so next thing about indices, which are a bit like logarithms, is because they're a bit like logarithms. So when we solve equations using logarithms, we use logarithm rules a lot. For example, we know that the log base R of AB equals the log base R of A plus the log base R of B, things like that. So those are useful. So we might then ask this question, like, does the same thing happen with indices, right? So I'm going to call this index rules. So and so the idea is this, is indices behave like logarithms, which we've kind of seen, but we want to clarify some more. But there's a quirk that arises. So just to sort of see what that quirk is, let's look at an example, right? So consider we know, this is the logarithm rule that I just mentioned, is that the log base R of AB is the log base R of A plus the log base R of B, right? So the following would be tempting. So it would be tempting to write the following, to write index base R of AB equals index base R of A plus index base R of B. This is tempting. This is, say, wish. But it's not quite right, right? So we can see an example. Right, so it's not this simple. It's pretty simple, but not this simple. So for example, suppose we do this. Let's let M be 14. This is the example we were just looking at. R be 3. And let's look at A is 13 and B is 5. So then what we have is then AB, because this is mod 14, AB is 9 mod 14. Right, it's 65, which is 9 mod 14. So then the wish statement would say the following. It would say that the index base 3 of 9 would be the index base 3 of 13 plus the index base 3 of 5. Now if you look up what those indices are, they're gone from this particular screen, but they're on the previous screen. This would say that 2 is 3 plus 5, and this is false. All right, 2 is absolutely not the same as 8. However, what you might notice is that 2 is congruent to 8 mod 6, and the 6 is the phi of 14. Now this kind of makes sense because we've seen before, we saw in 9.1 that the powers tend to operate mod the order, right? Like in this case, 3 to the x is congruent to 3 to the y if mod m, if and only if x is congruent to y mod the order, and the order is phi in this case. So this is reasonable. Right, this shouldn't come as a complete surprise. And in fact, so it leads to the following modification of the wish statement. Let's say the following theorem. So, theorem. So let's say let m be a modulus, R be a primitive root, and A and B be co-prime to M, and K will be a positive integer. We'll see what the K is for in a second. Just right now it's just a positive integer. So then this is what we get. So 1. And so for each of these, think of what this would say if it were a logarithm statement. So the first one says that the index base r of 1 is congruent to 0 mod phi of m. So the corresponding logarithm statement that's familiar would be that log base r of 1 is 0, which makes sense, right? Because you look at this and you're like, r to the 0 is 1. So yes, but now it's a modular statement. So the second one is the one that corresponds to what we just said. In other words, the index base r of ab is congruent to the index base r of a plus the index base r of b mod phi of m. And 3, the index base r of a to the k, there's a power rule for logarithms, is k, you can pull the power down in front, times the index base r of a mod phi of m. Now notice there's no, let's say, analogy for the logarithm statement that says a over b, because technically there's no division, right? You could write this as a times the inverse of b, because the b would have a multiplicative inverse because it's coprime to m, but typically we don't write it that way, so we just leave it just like this, and don't write an analogy. So this again is because there's no such thing as a over b. Like, formally speaking, there's no such thing as a over b. So let me prove 1 and 2. In the lecture notes online I proved all 3 of them, but 3 is very similar to 2. So let me just do 1 and 2 and we'll see, right? So for 1, by Euler's theorem, right, Euler's theorem tells us that r to the phi of m is 1 mod m. Right, that's exactly what Euler's theorem says. Right? And now the index, of course, is the unique power. It's the power between 1 and phi of m, such that r to that power gives us the value, right? So then by the definition of index, we simply have the index base r of 1 is phi of m, but that's the same as 0 mod phi of m. All right, so the first part of that statement follows from the definition of indices, this thing, and then this is just a congruence because it's mod phi of m. And that's it, that's the whole proof right there. So 2 is a little sneakier, but it's actually not difficult at all. Right? So 2 says the following. So first note that we're gonna note 2 things and put them together. Right? So if you take r to the index base r of ab, right, of course you get ab mod m. Right? This is congruence. Right? This is because the definition of the index is saying what power do I raise r to get ab, and then I raise r to that power, and I get ab mod m. Right? But also, if you look at r to the index base r of a plus the index base r of b, right? That sum. This is the same as r to the index base r of a times r to the index base r of b, because that's just when you multiply with the same base, you add the exponents. Right? And the first of these is a, the second of these is b mod m. Right? So the product gives us the same thing. So in other words, since, let me underline these in blue, since these two are equal, and since this is equal to this, and these are the same, the right hand sides are the same, what this tells us is that the left hand sides are the same. Right, this is congruent to r to the index base r of a times plus the index base r of b. And so recall from a theorem, we had a theorem in 9.1. We mentioned it maybe 10 minutes ago. This theorem said the following, said a to the x is congruent to a to the y mod m if and only if x is congruent to y mod the order base m of a, right? So in that case, here the order is phi of m, right? So this is phi of m if a is a primitive root. So by that, this statement up here, this statement right here, this guy becomes if and only if the index base r of ab is congruent to the index base r of a plus the index base r of b mod the order, which is phi of m QED. And so 3 is similar. I did it in the written notes, so feel free to take a look and see if you want to. So then last thing, right, before we actually do some calculations with this, I just want to mention this thing called the discrete logarithm problem. The book mentions this before, or mentions it after doing a calculation, but I think it's better to mention it before. And so the discrete logarithm problem is sort of interesting this way. If you're given a modulus, let's say, given a modulus m and a primitive root r, and then given an a with GCD of a and m being 1, we know that there's an exponent, right? Like we know that the index base r of a exists. Right? In other words, let's say that is, there is an x such that r to the x is congruent to a mod m. But how do you go about finding it? All right, so I mean, like what you could do is you could just try them all, right? You could be like, well, let me try r to the 1, right? And just for the reference, right, this x right here, this x is between 1 and phi of m. Because remember, the powers of the primitive root cover all of the coprime things using these powers. So you could say, well, let's just try them all, right? Try everything between 1 and phi of m, which seems pretty arduous. So you might be like, well, is there a shortcut? Right? And so the answer is, interestingly, is computationally not really. So in other words, any reasonable method of finding x is basically computationally equivalent to basically trying everything, which is really a pain. So in other words, more specifically, it turns out that there's no quick way. I'm not going to delve into the computational specifics of this, but there's no quick way to find x where quick means faster than simply trying everything. Up to phi of m. So now this is sort of interesting actually, because it turns out that certain encryption techniques are actually based upon this fact that taking exponents is quick, but taking logarithms is not quick. So this is not something we're going to look at right now, but the point I do want to make is that when we're working with these things, we typically will need to work out the logarithms ahead of time, right? So for us, we'll basically, let's say, need to preemptively work them out into a table. So for example, if m is 14 and our primitive root is 3, then we might use this table. We would use this table, right? We would make up a table, basically an index table, which lists all of the a's that are co-prime to 14. So that's 1, 3, 5, 9, 11, and 13. And then we would put the index down below. So these were all worked out earlier when we wrote down all those powers at the beginning. And then we would use these. All right, so just for reference, all these values, these were worked out by hand, by us earlier in this lesson. So when we do these arithmetic problems, we'll need to have a table available. So what I'm going to do next is I'm just going to sort of work through a couple of problems. I'm not going to use 14 and 3 because it's a very simple table. I use something a little bit bigger. And just work through some calculations and see how all these tools, these rules that we've learned can help us solve some problems. So final thing here, this is what we're called, oops, that wasn't supposed to be blue. Not that it really matters. Index arithmetic. And so basically let's solve some problems. And one thing I want you to recall here is this fact that we wrote down earlier. This will be used all over the place, other than the rules of logarithms or the rules of indices, which are like the rules of logarithms. Other than that, do not forget this that we wrote down earlier. We're going to be using this in a few different places. So recall this, right? And the rules, the index rules, which I'm not going to rewrite. And so let me just start with I'm going to do two examples. They're going to be based off the same modulus. So let's do this. Let's solve 3x to the 10th is congruent to 12 mod 17. Now, in order to do this, we need a primitive root mod 17. So there's a non-trivial step that has to happen, which I'm not going to show the work of. We could do this manually. We can do this by looking these things up. But the point is, first, we need a primitive root mod 17. So it turns out that r equals 3 works. In other words, i.e. the order mod 17 of 3 is 16, which is phi of 17. Or in other words, if you take powers of 3, you get everything that's co-prime to 17, which means basically everything 1 through 16, because all of those are co-prime because 17 is prime. Right. Now, this allows us to write down a table of indices. So this following table is non-trivial, right? Not at all. So what I'm going to do is I'm going to put this up at the top of the sheet because it's a bit long. So let me erase the other side and then I'll put it up at the top and then we'll keep going. Actually, now that I've erased, before I do, let me just make this one comment. So just to be clear, the way that we find this is by taking all the powers of 3 and seeing what we get, right? So we do this. So we do 3 to the 1, 3 to the 2, 3 to the 3 up to and including 3 to the 16. We do all of those mod 17. And then for each we get an index statement. So for example, 3 to the 3 is 27, which is 10 mod 17. So the index base 3 of 10 is 3. And so altogether, we get the following. So let me put this up at the top right hand side. We're going to get A. Sorry, little crappy there. I'm going to get A, and I'm going to get the index base 3 of A. And so we need to be careful because we can get everything from 1 to 16. So I'm going to fill these in as we go. So this is actually in the book. I just stole this example, but this could be worked out by hand. Not easily, as we mentioned, right? The entire point of this is not a trivial process. So we have 6, 15, we have 7, 11, we have 8, 10, we have 9 and 2, we have 10 and 3, we have 11 and 7, we have 12 and 13, we have 13 and 4, we have 14 and 9, we have 15 and 6, we have 16 and 8. Now, for the record, some of these are actually pretty obvious, right? So, or at least like this one we just did, this one right here, the index base 3 of 10, that's the one that's right here, right here. Something like, say, this one's really obvious. This is because 3 to the 2 is 9 mod 17. So some of these are fairly easy to see, but some of them are not at all. So then first, let's get back to our problem. So the first thing we're going to do is we're going to take the index base 3 of both sides. Basically. Essentially, we're going to use this thing right here. I'm going to make that the red. We're going to use that. So what happens when you take the index of both sides? The modulus changes, right? So we get the index base 3 of 3x to the 10 is congruent to the index base 3 of 12, but now it becomes mod 16 because this is phi of 17. So this is a place where people make the most mistakes, or make mistakes first, is they forget to change the modulus, right? So the modulus, when you take the index, becomes phi of m instead of m, right? Then we rip it apart using the rules. So 3 times x to the 10, we can split with addition. So think logarithm rules. So we get index base 3 of 3 plus 10 index base 3 of x is congruent to index base 3 of 12 mod 16. Then we fill in the values we know. This is from the table. So the index base 3 of 3 is 1. Right? So I'll label all these in a second where they come from. I have 10. I have the index base 3 of x, which we don't know. We have the index base 3 of 12, which is 13. So just for reference, let me find a nice color. Purple's good. Let's say this guy right here, it becomes this guy. That's from here, right there. And then let's say light green, and this guy becomes this guy, and that's from right here, light green. So then we solve a little bit further. We go 10 index base 3 of x is 12 mod 16. And so now, right, this is basically a linear congruence where index base 3 of x is the variable, right? So if you think of this guy right here as a single variable, with index base 3x as the variable. In other words, think of this as 10, say, y is congruent to 12 mod 16. Like, you don't need to write it this way, but think of it this way. Because when you think of it this way, then we know from earlier stuff that the GCD of 10 and 16 is 2, which divides 12. So there exist two incongruent solutions, mod 16. Right? So we can find those using methods that we have had before. So I'm going to omit those for a second. Or rather, I'm going to omit the explicit calculation of the solutions. So this guy, I want to leave that that red thing up there. So I only erase this bit. Right? So this, in other words, this guy right here, this guy has solutions y is congruent to 6 and 14 mod 16. If you've forgotten how to do that, you may need to review back into that section, right? So in other words, i.e., this tells us that the index base 3 of x can be 6 and 14. Because remember, y is just a stand-in for index base 3 of x. It's just sort of a little thing to remember what we're solving for. So then what we do is we reverse the table. So we reverse lookup in the table. That is, we unindex with the table and also with the red thing again. So in other words, we use this fact again. That's still up there, which is why I wanted to leave it. Right? So we say like, well, which x gives us an index of 6? Right? So I have colors all over the place here, but that's all right. So if we say like, which thing has an index of 6 right here? So we go, well, if we look on our table, that's right here. And then we say, which one has an index of 14? And we look on our table, and that's right here. So as a consequence, when we sort of look things up again, or backwards look things up, we get x is congruent to 15 and 2, and this is back at mod 17 because we sort of unindexed using the red thing, right? So now we've got our final solutions, mod 17. So that's the first of two problems. I want to do one more, but that's actually sort of the more complicated of the two, right? So again, we start at the very beginning, we take the index of both sides, we rip it apart using the rules, we look up the values we know, we treat the result like a linear congruence. We solve for the index base 3 of x, and then we reverse look up to get x. Now, the second problem will actually be a little bit different. It'll turn out to be a little bit easier. And don't think about why, rather just think about how the calculation works. So, second example. Let's solve 4 to the x is congruent to 16 mod 17. Now it's tempting to think that 2 is the solution because 4 squared is 16. And it may be the solution and it may be the only solution, but there may be some modular statements involved. So let's work this out. So what we're going to do is the same thing as before. We're going to start, we take the index of both sides. Base 3, because that's our primitive root. We're using the same table. So we get the index base 3 of 4 to the x. Index base 3 of 16, mod 16, because the phi changes, or the modulus changes to phi of m, again using the asterisk. Red asterisk is being used right here. Same red asterisk that's on the screen. So then we bring the x down in front. And then we can fill in the values that we know. Notice here, in the previous question, the index, the x had an index wrapped around it. We can still see that over here when we solved it at the end. In this one, it doesn't. It's sort of free and clear, right? So we keep going. We look up the index base 3 of 4, and we get 12. The index base 3 of 16, and we get 8. So we can tidy this up. 12x is 8 mod 16. And then what we can do is we can use the fact that we can divide out both sides by 4 as long as we divide 16 by the GCD of 16 and 4. So remember the rule we had that that we have. I'll write it over here. If AX is congruent to B, actually let me write it the way it should be. Is that we officially had that if AB is congruent to AC mod M, then I can cancel the A, provided I divide the M by the GCD of A and M. Right? So this is sort of from way, way, way back. So what I'm going to do here is divide both sides by 4. So in this case we get 3x is congruent to 2. This becomes 16 over the GCD of 16 and 4. Which is of course 4, but just to make sure it's clear. So this is 3x is congruent to 2. 16 over 4 is 4. And we get this. This has one solution mod 4, right? And that solution is x equals 2. Right, this is unique mod 4, right? So this is our solution, right? Because we've got an x at the end. Now, so two things to note is we don't want to say that 2 is the only solution, right? 2 is the only solution mod 4, but there are many solutions. Right, for example, you could write, say, if you wanted to do it without mod, you could have 2, you could have 6, you could have -2, you could have -6. That's the first note. Second note is that in the previous problem we had to sort of unindex, right? Like over here. The reason for this is that the x was wrapped inside an index and we had to get it out. Here the x isn't, right? So here we don't need to unindex because the x is not inside an index. Right, it's free and clear. In other words, we have x equals 2 mod 4. X is congruent to 2 mod 4. There's nothing that needs to be done to get a hold of x. We're already there, and that's the end of the problem. That's the end of the section.